Alright guys, today we're going to be talking about symmetry. We have a couple learning targets today. Our goal is to determine if a figure has line symmetry and also to determine if a figure has rotational symmetry. So we're going to be dealing with two different types of symmetry, again line symmetry and rotational symmetry. So let's go ahead and get started. Now we have this flower here, this pink flower, and we're wondering how many lines of does this flower have line symmetry or does it have rotational symmetry? Now, as we look at this, we may notice a few things, and we need to be really exact in this. So if you notice here, it kind of curves along this edge. And it does the same thing on each petal. So if I were to fold this over a line, it would not map perfectly onto itself because these little curves here, because it's not the same curve on either end. So it's not going to map itself perfectly on top of itself once again. So in fact, these do not have lines of symmetry because, again, these little curves are throwing it all off. It makes it so that it would not map back onto itself if we folded it perfect. However, if this was perfect on each side, we could draw multiple lines of symmetry through this, such as this blue line here, this blue line here, and so on and so forth. So we can actually see some lines of symmetry that could occur here if it was perfect on each of these little circles. So this flower does not have line symmetry, unfortunately, due to these small imperfections. Now, does this have rotational symmetry? Well, we can determine that. And to do that, we go ahead and we take our point right at the center. So we're going to take a point right at the center of our figure. And we're going to try and spin our figure around in a circular motion here. So we're going to go in a circular motion. Now, there's 5 petals here, and each of these petals is supposed to be symmetric. They're supposed to be the same as the petal right next to it. So, if that's the case, then I can move this one petal 72 degrees to get to my next petal. Now, I may be wondering, how did I get 72? Well, we know in a full circle there's 360 degrees. There's 5 congruent petals. So 360 degrees, but divided by those 5 congruent petals will give us 72 degrees. So that means that it's 72 degrees between each petal. So get from one petal's point right here to the next petal's point right here, this angle at the center that's created, this red angle here, that is 72 degrees. So this goes back to what we were talking about in rotations in our last video, and how rotations are going from a point to our center of rotation to our image. So we have our pre-image, our center of rotation, and our image creating this 72 degree angle here. In fact, I can do that with any 2 points on this figure. So I can say from here to here, that would give me another 72 degrees. So this is also 72 degrees. So each one of these will give us 72 degrees, and of course if we have 5 of these, 72 times 5, 72 degrees times 5 will give me 360 degrees total. So it makes sense that I went in a full circle with 5 congruent petals. All right, so let's go ahead and talk about these definitions. Now, we say a figure has symmetry if there is a rigid motion that maps the figure onto itself. Now we know that we have 2 types of symmetry. We have line symmetry and we have rotational symmetry. Now, line symmetry will deal with the rigid motion of reflections. That deals with reflections. Meanwhile, rotational symmetry will deal with rotations because we're rotating. So it says if there's a rigid motion that maps the figure onto itself, it has symmetry. But the symmetry that we're going to be looking for is both line symmetry, so reflections for the rigid motion, or rotational symmetry, which is a rotation for our rigid motion. So those are the 2 rigid motions that we'll be playing with. We will not be using translations at all during this, so keep that in mind. Translations are the only rigid motion that we will not be working with during this. Now, I can still prove that 2 figures are the same, 2 figures are symmetric based upon a translation, but it'd be more than likely a sequence of transformations to determine it. So it'd have to deal with a reflection or a rotation at some point. So we say a figure has line symmetry if there is a line that reflects the image onto itself. And again, here's that keyword reflects, because that is the rigid motion that we'll be using. So we're reflecting for line symmetry. Now, these lines of reflection that we create, these are going to be called lines of symmetry. So when we draw our line through our figure, because with symmetry we're going to be drawing through our image itself, those are going to be lines of symmetry as well, because they're making our figure symmetric to itself. So, does this triangle have line symmetry? Go ahead and pause the video and answer this if you'd like, and we'll go through it in just a second. Looking at this is an isosceles triangle. So I know that because we have two base angles that are congruent. These two angles right down below here, these two angles are congruent. So this is a triangle called an isosceles triangle. Now, hopefully you guys have heard of this before. If you haven't, that's okay. We will be dealing with isosceles triangles a little bit later on in this course. But know that if you have two angles, two base angles that are congruent, so this angle is congruent to this angle, we call that an isosceles triangle. Now, isosceles triangles do have one line of symmetry, and it goes straight from the top point down to the midpoint on the opposite side. So it's going to make sure that it hits the midpoint down here, so that it splits it perfectly in two. And this angle is congruent to this angle, so it should map perfectly on top. So yes, this figure can be folded onto itself with this purple line here. This purple line is our line of symmetry. It's our line of reflection, but again, if we're dealing with symmetry, we call it a line of symmetry. It's making this figure symmetric to each side. All right. Now, go ahead, pause the video, try these three out real quick, and see if you can find all the lines of symmetry for each figure. Now, if it doesn't have any symmetry, just write no symmetry. Okay, so looking at this one, the first shape that we have here is a rectangle. Four right angles, opposite sides are congruent. So, looking at this, we can draw two lines of symmetry through here. One hot dog style, if you remember folding papers back in elementary school, one hot dog style, one hamburger style. So we have two lines of symmetry here. Now you may be wondering about these red lines that I'm about to draw. If I have this red line here, is this a line of symmetry? Well, no. If you guys ever made paper airplanes in the past, you probably have tried to fold your paper over diagonally like this. And what you realize is that this side does not map perfectly onto this side when you fold it like this. So these diagonal lines are actually not lines of symmetry at all. And so that would be a common error that I see pretty often, is where people draw diagonals as lines of symmetry when they are clearly not. The second shape that we have here is a scalene triangle. Scalene triangles just mean that all sides are not the same, and none of the angles will be the same either. So they're all individualized line segment lengths and all individualized angles. So none of them are the same. Now, if that's the case, if nothing's the same there, then there's going to be no lines of symmetry. There's no symmetry occurring because nothing's the same. It's not going to fall on top of itself perfectly if nothing's symmetric. And then lastly, we have this L shape here. This L shape actually has one line of symmetry, and it goes straight through this diagonal. If I were to fold across this diagonal, we would find out that this side maps perfectly onto this side. So there is indeed one line of symmetry here. All right, so think about this for a minute. Pause the video if you need to think for a minute. But what figure has an infinite number of lines of reflection, these lines of symmetry that we're dealing with? Which figure has that? Well, the figure that would have that is a circle. No matter what, this circle is going to have an infinite number of lines of symmetry, lines of reflection here. And the reason that is because no matter where I draw my line, as long as it goes through the center point, that will be a line of reflection. Now, along with that, if I even go 0.000000, and I can keep writing as many zeros as I really want to, 1 degrees. So if I go just one little tiny fraction of a degree up, that's still a new line of symmetry. So it doesn't matter how many degrees I go up, even if it's the tiniest amount, it will create a new line of symmetry for us. So a circle will always have an infinite number of lines of symmetry. Next, we're going to go ahead and move into rotational symmetry. So a figure has rotational symmetry if there's an angle measure from 0 to 180 degrees so this is really important, 0 to 180 degrees, that maps the figure onto itself. So our angle of rotation must be greater than 0. It can't be equal to 0, because if my angle measure that I'm rotating is 0 degrees, I'm not moving at all. It's not an actual rotation. So it needs to be greater than 0, but less than or equal to 180. So therefore my angle measure, I'll just use the Greek letter theta. Theta is used often for angle measures. It's a variable that is exclusive to angle measures. So my angle measure must be greater than 0, but less than or equal to 180 degrees. If that rotational degree is within that range, then we say that we have rotational symmetry. And again, this angle measure needs to map the figure back onto itself. It needs to look like the exact same figure that we started with in order for it to be rotational symmetry. If it doesn't look the exact same, it is not rotational symmetry. So, looking at the star here, we have an angle of rotational symmetry of 72 degrees. Now this is going to be very similar to the one that we started with earlier today. As we can see, I have 5 congruent points on this star, each of these little triangles on the end. So if I have 5 congruent pieces, and I know that there's 360 degrees within a full circle divided by the 5 congruent pieces, well, that will give us 72 degrees. So that's where the 72 comes from. In fact, just to make it a little bit more clear, if I were to draw points on each of these tips here, each of the tips of the triangle, and I were to connect those points with my center of the star, so my center of rotation, well, we'd see that this blue angle is 72 degrees. And in fact, every single one of these angles that we can create here is 72 degrees. So again, here it is, 72 degrees here, here, and so on. So that is why our angle of rotation is 72 degrees. Because in 72 degrees, when I rotate it, this point will map right here, and it will look like the exact same image that we started with, which is what we're looking for. So go ahead and take a minute, pause the video if you need to, and try and determine whether each of these has rotational symmetry. If it does, please give me the angle of rotation that's less than 360 degrees. All right, so looking at this first picture, we have a square. I know that because all sides are congruent and we have 4 right angles. So looking at this, we should have 1, 2, 3, and 4 lines of symmetry. Now you may be wondering about these diagonals right now. It doesn't work with a rectangle, but it works with a square. And the reason why that is because all sides are congruent here. So therefore, oh, my bad, I was thinking line symmetry still. For this one, my bad, we have 4 congruent points, 360 degrees to travel in a full circle. So 360 divided by those 4 points gives me 90 degrees of rotational symmetry. And also we have 4 lines of symmetry. But that's neither here nor there. Next, we have the scalene triangle. Again, nothing on a scalene triangle is the same. So therefore, there should be no angle rotation that I can do to map this figure back onto itself besides 360 degrees. And again, we got to remember that our angle measure must be greater than 0, but less than or equal to 180 degrees. So if it's a 360 degree rotation, that does not count. This one has no symmetry, that scalene triangle. Then lastly, we have this arrow here, this arrow on both sides. This is the same as like an equivalent sign in mathematics, except it's rotated 90 degrees, so it's pointing up and down. Now, looking at this, I have 2 points. I know that there's 360 degrees in the full circle, so I can do 360 divided by 2, which will give me 180 degrees. And as we can see here, this is the max that we can go for our rotation, 180 degrees. If I go beyond this even by 0.01, it is no longer a rotational symmetry problem, because again, our limit is 180 degrees. And if it did go to 181, I would just write no symmetry. All right. So again, a figure may have line symmetry, rotational symmetry, both, or no symmetry. So it's really up to the problem itself and the figure that you're dealing with. Now, if you find line symmetry on a figure, line symmetry, there's a couple things that they may ask you for. And these things are typically pretty straightforward. They'll ask you how many lines of symmetry, and then they'll also often ask you the equation of the line, of symmetry. So when it asks you for the equation of the line of symmetry, it's either going to be asking for y equals mx plus b, slope-intercept form. It may ask you for a vertical line or a horizontal line. So a horizontal line such as y is equal to 2 or 4 or 6 or whatever number it is, but this is a horizontal line. Or it may ask you for a vertical line, which is x is equal to a number. I'm not sure what number it could be, but let's just throw a random one in so you can see what it kind of looks like. So x is equal to 3. This is vertical. This is a vertical line. So it'll either give you a slanted line, y equals mx plus b, a horizontal line, y equals a number, or a vertical line, x equals a number. These are the equations that you'll use if they ask for the equation of the line of symmetry. And again, it shouldn't be too difficult. You should be able to look at it and see where you should cut it in half. Now, if we're given something such as rotational symmetry, they will also ask for some things. The most common thing that they'll ask for with rotational symmetry is the angle of rotation. So how much we're rotating. The other thing that they'll ask is the point of rotation. So what point am I rotating around? Now, oftentimes the point of rotation is found in the center of our figure. Sometimes you'll need to determine where you need to rotate the figure in order to make it work though. So this is going to be totally dependent upon the problem itself as well. What point are we rotating around? And again, more often than not, if it's a solid figure, we're going to be rotating in the center of it. Not always, but often. So keep that in mind. They'll ask for the angle of rotation, so 360 divided by however many congruent pieces. And then they'll ask for the point of rotation. At what point are we rotating around? So keep an eye out for both of these during line symmetry and rotational symmetry, and that way you guys are good to go. Now, if it has both, you may need to give the equation of the line and the point of rotation and the angle of rotation and how many lines of symmetry. So again, if it's both, you got to do a bit more work. If it's no symmetry, then they may still ask you for line symmetry and rotational symmetry measures. There should be an option in those questions where you can say this doesn't have symmetry. And that's all you'd have to answer for that. So if you answer no symmetry, you may have to say no a couple more times in the question itself to make sure that you're answering it fully. So keep that in mind too. All right, so go ahead, pause the video for a sec if you'd like, and describe the symmetry. I'm looking for lines, I'm looking for rotational, I'm looking for both. So go ahead and describe the symmetry here. All right, so looking at this, we can tell that we have some line symmetry happening. I can see that I can draw a line diagonally here. Same thing on the other side, diagonally here. I can go straight through the center. That's not that great. Straight through the center, or I can go straight through the sides horizontally. So from here, I need to count how many lines we have. So looking at this, we have 4 lines, 1, 2, 3, and 4. Now be careful here, because a common occurrence that is just a common mistake that is very easy to avoid is people will count their lines twice. So people will go 1, 2, 3, 4, 5 lines. Or they'll go 1, 2, 3, 4, 5, 6, 7, 8. But again, the line goes all the way through forever. So it'd be 1, 2, 3, and 4 total lines. As for our rotational symmetry, I see that we have 1, 2, 3, 4 congruent pieces. 360 degrees divided by 4 congruent points will give us 90 degrees of rotational symmetry. And in fact, we can actually see, if I take my center of rotation, the middle of our figure, and I were to draw segments to each of these points, we can see that it creates this 90-degree angle here as well. So from our pre-image to our center of rotation to our image creates that 90-degree angle. And that will work for any 2 points that I choose on here as long as they are right next to each other, as long as they're adjacent points, adjacent congruent parts. So keep that in mind too. All right. Last one, go ahead and pause the video real quick if you need to and explain the error here. A student was asked to draw all the lines of symmetry. All right, so looking at this one, a student drew a couple good lines of symmetry, the vertical one and the horizontal one. However, they have these diagonal lines here, and I'm going to go ahead and outline those in red. They have these diagonal ones here. And we know that these diagonal ones don't fold over perfectly. In fact, if you don't believe me, take a piece of paper and try and fold from diagonal to diagonal and see if this triangle is the exact same and folds over perfectly onto this triangle. It doesn't. So therefore, the diagonal lines are not lines of symmetry. The reflection will not map the figure onto itself if I go over these red lines. With the black lines here, it will work, but the red lines, it will not. So keep that in mind. All right, so we have now we can now determine if a figure has line symmetry or rotational symmetry, and also answer some follow-up questions about lines that we can draw through those, as well as the center of rotation and the rotational degree amount as well. So keep all those in mind. If you guys have any questions, let me know. Other than that, I hope that you guys have a great rest of your day. Thank you guys so much for watching. Take care.